Okay, so I guess we can start. Hello, everyone. My name is Gabriele Bavota, and it's my pleasure to chair this session about recommended systems. We have 6 papers that will be presented. 4 are from the research track, then we have 1 near paper and 1 from the software engineering in practice track. As you probably know at this point, the format is the following. We will have the 6 presentations, one after the other, 5 minutes each. And then we will have an open discussion with Q&A. Feel free to write in the chat and then we'll read the questions, or you can just unmute yourself at the end of the presentations and ask any questions you want, okay? So we start with the first work that is presented by Martin, and it's about modeling source code for learning, for automating code-related tasks. So Martin, feel free to go.
Okay, thank you for the introduction, Gabriel. So my name is Martin, and I'm a PhD student at University of Montreal, and this is a presentation of our near-track paper, Better Modeling the Programming World with Code Concept Graphs, Augmented Multimodal Learning. So let me start right off with context and motivation of this work. When it comes to deep learning-based recommender system, the state-of-the-art learning paradigm is the following. So usually it consists of 2 phases. The first phase is a pre-training phase. That can be multilingual or unilingual, where we have a transformer-based model that learns general-purpose code vector representations. So these code vector representations are not ready for the downstream task. So we have a second phase that is about fine-tuning, where we fine-tune the transformer-based model on data that are task-specific. So examples of tasks are left-to-right code generation with models such as CodeGPT or Codex. Second task is code search with CodeBERT. And a third one is code summarization with CodeT5, PLBART. And of course, there are many other tasks where these models perform very well. And so these deep learning models, they show great robustness and generalization on different data distribution and tasks. Because they are based on the transformer architecture, they learn mostly from syntax because the inputs are sequences of code tokens, and they also learn from the global information of these sequences thanks to the self-attention layers in the transformer. And in this work, we claim that these programs are concept-based. So that is, from the input code, we can extract concept graphs that can highlight high-level relationships between identifiers. And that makes actually programs very multimodal, where instead of learning from one source of information, we can actually leverage multiple levels of abstraction in the learning process. And so the whole point of this work is, can we learn better representations of code using multimodal learning? And we came up with a multimodal learning approach with code concept graphs, where the idea is to joint learn a BERT-like language model and a graph neural network. So the graph neural network is based on concept graphs, and the BERT-like language model is based on the code tokens. We show the applicability of this approach to code search, where the objective is to find the best code candidate given a natural language query. And we show that it works quite well with simple fusion of the code and the concept graph representation. So given a data set of code and documentation, we extract the concept graphs and the code tokens. We get a representation of the concept graphs using the GNN, and we get a representation of the code using the language model. We use a simple fusion to get the output representation that is compared using a distance loss function with the query embedding. And so with this approach, we show improvement over CodeBERT, which is a strong baseline. So to conclude this presentation, I just want to highlight a few questions that I might hope open the discussion. So first one is, currently we have large pre-trained models of code that are only based on sequences of tokens. Can we have large multimodal pre-trained models of code to learn general purpose code representations. Another question is, should we fine-tune existing pre-trained models in a multimodal fashion, such as we did in this work? In that view, we could define task-specific modalities for the fine-tuning. And another interesting discussion could be about the scaling law. So broadly speaking, the scaling law states that the more parameters we add to the network, the higher the accuracy on the task we will get. So we can derive a few questions from that. Can we observe the same trend with multimodal learning? How does multimodal learning compare to unimodal learning with respect to this law? And finally, are the data processing and fusion in the learning process worth the time and resources? So there is probably a trade-off to think about here. So to end this presentation, here are my dear co-authors, so the Professor Houari Saori and the Professor Beng Liu from University of Montreal. If you have any question in this session, feel free to ask. And I will be very happy to discuss this topic with you. Thank you.
Thanks a lot, Martin. Excellent talk, perfectly on time. Okay, we can move to the second paper that will be presented by Julian, right, about code review recommendation. So yeah, they basically tested code review recommendations in practice, right, in industry. So let's see what happened. Please. You are on mute. You are on mute. You are still on mute. We can't hear. You are on mute. I don't know if I can unmute him.
Oh, sorry. Can you hear me? Is my voice fluent? Oh, okay. Hello, everyone. I'm Julian Chen from Zhejiang University, and my presentation topic is code review recommendation in Tencent, practice, challenge, and direction. And this work was collaborated with Gongfeng SAI Lab at Tencent. First, I will introduce why does Tencent need such a recommendation system. As we all know, Tencent is a giant company. It has many business organizations, and these business organizations are divided into small developing teams. In general, members in small teams do not need such a recommendation because they are all familiar with each other, and they can find the code reviewer very easily. However, recently, Tencent is performing an inner source practice. Tencent established many virtual organizations across different groups. That means developers come from all over the company, and they are not limited by the divided teams. It seems like an open source practice, and in this environment, a great many code changes are submitted every day, every week, and every month. On average, there are about tens of thousands of commits, and who should review these commits become a big problem, not as before. For example, the related maintainers are all familiar colleagues, and you don't know who should review these commits. After all, there are about 100,000 of employees, and about 30% are developers. So we are investigating deploying a real recommendation system. And at Tencent, developers use an internal code review system called Gongfeng, and the recommendation system is intended to embed it into the workflow. And that is the step 3 and step 4. So there are many existing code review recommendation system approaches, but we wonder what is their effectiveness of code, and we wonder if they works at Tencent. As we all know, existing approaches in literature are limited by experiment environments. For example, some models cannot profile developers as there's no data, or it may concerning the privacy. But in practice, we can access public information as much as possible. And second, as a real recommending system, and we perform the interviews considering what are the perceptions and the expectations of practitioners on such a code review recommendation system. And our research methodology consists of 2 parts. The left is the experiments, and the right is the interview. And our interview guide can be found on this URL. And in summary, the first research questions has 3 findings. The first findings is that existing approaches do not perform so well on the 10 selected projects in Tencent. We can see that the red and the orange rectangles, the open source projects, the algorithm on the open source projects has a much better performance on those on the 10 selected projects. And the second finding is that projects with dominant reviewers can get good performance. What is dominant reviewer? They are often tech leaders or senior developers. However, even though we find that it is easy to recommend a correct reviewer, but it is a little hard to alleviate their burden because they may receive many notifications every day and they cannot review all, even though they are correct reviewers. And the third finding is that code start problem and code review recommendation approach suffers from code start problem, and they perform badly when initialized for several weeks. And for the second research questions, we had many detailed opinions. And in summary, we can see that practitioners are confident about the machine learning-based code review recommendation approaches. And they also consider many more factors. For example, they may want the reviewers familiar with code to help them to gain knowledge or to help them to improve the ability. And for the time limitation, there are more detailed opinions. So please refer to our preprint or our full video. And you can see it on my website or contact my email and or after the discussion. And thank you.
Thanks a lot, Kuyan. Nice talk. So we can move to the next speaker, who is Wenxin, presenting recommending good first issues in GitHub open source projects. Okay, we see the screen. Perfect. Feel free to start.
Okay. Hello, everyone. I'm Wenqin Xiao, a PhD candidate from Peking University. Today, I'm going to introduce our work about recommending good first issues in GitHub OSS projects. Nowadays, open source software has become quite important in our society. If our upstream repositories are poorly maintained, projects using them may face potential risks. For example, bugs will not be solved. One major challenge of OSS sustainability is to attract and retain capable newcomers. A good influx of newcomers can resist the crisis of project sustainability caused by the loss of developers. GitHub recommends projects to use the good first issue label to tag issues that may be suitable for newcomers. The newbies who are searching for potential suitable issues can choose a project and look through issues with GFI labels to find one to contribute. However, according to previous work, the GFI mechanism faces some challenges. The first is that GFI label is rarely used. The second is that only very few issues marked as GFI are really solved by newcomers. To solve these problems, we propose an automated approach to recommend GFI. It can reduce the burden of manual labeling and the false labels due to misjudging of new labelers. The goal of this work is to identify issues, projects, open issues that may be suitable for newcomers. Instead of using GFI label to set the ground truth, we regard issues resolved by newcomers are suitable for them. Besides, the developers made no more than K commits for a project is a newcomer for the project. We collect the data from 3 sources. Content include issue title, body, and labels. Background include reporter and project-related data. And the dynamics issues include data from discussions and events. Then we choose XGBoost to train our model because it outperforms other models in our experiments. We use GHTorrent and GitHub API to collect data. We identify the top 100 repositories with the most GFI signaling label. We only collect issues closed by pull request or commits. We collect the data at 2 time points, when the issue is just reported and before it is assigned. In research question 1, examine the model performance. Table 1 shows the performance under different thresholds. The model achieves more than 0.8 AUC for the second time point. Figure 2 shows our model distinguishes issues well. Then we compare baselines and variants of our model. Our model achieves best performance with XGBoost, and the reporter-related features seem to be the most important indicators. In RQ2, we find that issues reported by a developer with just enough experiments, document type issues, and issues involved with experienced developers are more likely to be solved by newcomers. In RQ3, we check if our method is helpful in a real-world setting. We report potential good first issues, and 16 issues are confirmed as suitable for newcomers. Here are some feedbacks for our reports. Developers are positive about the automatically recommended. Here are contributions. First, we formulate and define the GFI recommendation problem. Second, we analyze the features of GFI. Third, we propose a tool to recommend GFI and verify its good performance. At last, we provide a public GitHub issue dataset. You can find our artifact at the GitHub link. Thank you for listening to my presentation.
Thanks a lot for the nice talk. We can move to the fourth one, that is by Hongyu, and it's about recommending reviewers.
Okay, let's wait a minute. Sorry.
Remember to write questions in the chat if you want. I will ask them later.
Okay.
Wait,
yes.
We don't see your screen. We don't see your screen.
Oh, okay. So let me try that again. Okay, the entire screen. Okay.
Okay, loading.
Okay.
We see the screen.
Okay.
Perfect. Go on.
Okay, let's get started. So, hello everyone. I'm Kwang Hongyu, and I'm very happy to represent our team to present our paper that is modeling review history for reviewer recommendation hypergraph approach in the EKC conference. So let's get started. So code review has been playing a key role in software maintenance and evolution for both big IT companies, corporations such as Google, and also for the open source community. So recommending suitable reviewers can greatly improve the efficiency of code review. That I was talking about was reviewing the pull request. But specifically, the reviewer recommendation is especially challenging in context of open source projects due to the loose organizations, especially compared with the large corporations. So our researchers now try to propose a set of automated recommenders based on modeling the review history. It's basically build a model from the historical review. So when a new pull request comes, so the model could recommend a candidate list, including the potentially suitable reviewers, so that the manager could just go through the list and find the suitable reviewers instead of searching the entire project. And the recent research also shows that the graph-based modeling is quite promising in this research, because that is to build the graph based on the historical reviews. This kind of research direction is promising because it can draw strengths from both proposed heuristics and learning algorithms, and more importantly, it's a natural way to model the reviewers' collaborations when they are reviewing the pull request. But however, modeling through the ordinary graph is difficult to depict in-depth collaborations. That is the reviews with 3 or more reviewers in review history. And we argue that it is quite common in recent practice, because we did some investigation and we found that 71% of pull requests are reviewed by at least 3 reviewers in TensorFlow project. And we also found that there are 2 PRs are reviewed by up to 22 reviewers. So this is intensive collaboration, right? And if we see a 4 reviewers review, and if we want to model that in the ordinary graph, it will be a complete subgraph with about 6 edges. And for the algorithm, if we consider each edge at a time, each edge will only capture part of that intensive collaboration. So we propose to use the hypergraph instead. So in the hypergraph, the biggest difference lies in the the edge. If for example, if the 4 reverse review will need 6 edges to model, but in the hypergraph there will be only 1 hyper edge that covers the full node if the node are the reviewers. So we think that is a much more efficient way to model the historical reviews. And during our research, we also concern an additional issue is that the workload issues, because review histories show that only a few core reviewers do most of the reviews. That's the fact, and that's the actual histories. So if we build recommenders from that history, if we put that into use, so these automated recommenders will further increase core reviewers' workload. So when we were presenting our approach, we also expected to recommend diversified candidate reviewers by using the hypergraph to model review history and introduce the recommendation diversity metrics in our evaluation. So let's quickly go through our approach. The first step, the first important step is the construction of the hypergraph. So we were modeling the known pull request. There are 3 vertices, 3 kinds of vertices in our graph. That is the contributors shown in red, and the pull requests shown in blue, and the reviewers shown in green. And we have the normal edges between the contributors and the pull request, and also the hyper edge that decrypting the collaborations that is between the pull request and reviewers. Then we have derived edges from the file path similarity between each 2 of the pull requests. If they are similarly enough, we'll put another edge between them. And for a newly proposed pull request, we will add a new pull request vertex and also a new contributor vertex if the contributor is a newcomer. And also we will add possible edges. We will add possible PP edges similarly to the previous work. So with the constructed hypergraph, we need to weigh the edges and the hyper edges. We basically can consider the three factors. The first is between the contributors and the pull request, it is when the PR is submitted. Between the pull request and the viewers is the number and time of all reverse comments. And between each two of the pull requests is the file path similarity, and along with the time gap of the two submissions. So with the weighted graph, we can now do our ranking algorithm by the hyper-based machine learning technique. So in general, the score of each vertex is computed based on edge and hyper edge weights, as we has discussed. And also we will optimize the scores of all vertices in the graph, including the newly added ones. So we will always do that with optimization with our proposed cost function. So our experiment is based on is compared with 6 baselines and works on 12 projects from the time like 2017 to 2020. And we set up 3 metrics, that is the top K accuracy representing the common accuracy, the MR for the same reason, and also the recommendation distribution. So the experiment shows that our proposed approach can achieve the best accuracy at the top 3 and also achieve relatively good RD metric. So that's the conclusion of that's the results of our experiment.
Thanks a lot.
Okay.
Okay, so we can move to the next one. Please let me check. Chao, who is going to talk about shell fusion.
Okay.
Please share the screen.
Mm.
Okay,
okay?
Feel free to start.
Sure. Well, I'm Chao Liu from Chongqing University, and I'll present our work, Shell Fusion, answer generation for shell programming tasks via knowledge fusion. Well, shell programming is widely used in various platforms, such as the Linux systems, and there are over 50,000 shell commands documented in the official meta pages of Ubuntu. And the challenge is, given a shell programming task, how to quickly find appropriate shell commands and the corresponding scripts. And we usually have 3 sources. The first is a manual page document in the official website. But the meta page is very lengthy to read and the lack of examples to use the command. The second source is the TLDR document in the GitHub, and it is very easy to use. It presents some very useful example and with descriptions, but it only covers a limited number of shell commands. And the example is very simple to use, just for beginners. A lack of explanation for commands and options. And the third choice is question and answer data, such as Ask Ubuntu and Stack Overflow. Also, there's question and answer data, lack of explanation of commands and options. Well, from these 3 sources, we have the motivation how to effectively address the challenge in shell programming by fusing useful knowledge from those 3 kind of resources. And we present our work, Shell Fusion. It consists of 2 parts, offline processing and online answer generation. And the offline processing aims to collect the data from 3 different sources. We obtained shell-related questions from 4 question-answer communities, such as Ask Ubuntu and Stack Overflow. And we obtained shell commands from official menu pages, like the example below. And we obtained the shell command from TLDR tutorials. With these three kind of documents, we generate answers, generate answers from it. For query describing a shell programming task, we first retrieve the top similar descriptions by using the Newsoning and word embedding approach. And we detect the shell commands with options from the scripts connected to the questions. And we filter irrelevant commands and return the only top key commands as candidates. And we re-rank the commands according to the similarity to the query and questions. And finally, we fused the generated answers with a comprehensive answers. It has 4 parts: a many-page summary, and TLDR task script pair, and the answer from question answer communities, and the explanation of the options of the official many pages. And in our experiment, we first set the best setting of our K from some randomly selected queries. And then we compared shell fusion with the best existing baseline Maglin and 3 variants of shell fusion. The results showed a significant improvement. And we proved that shell fusion is very efficient to use. It costs only 0.4 seconds per query to answer generation. Finally, we evaluate the usefulness of our tool with 20 participants and on 4 representative queries. From the generated answer, there's 3 examples, and the feedback says that our generation is comprehensive and easy to read and very useful. And finally, we can show that shell fusion can help programmers address the programming tasks more efficiently and accurately. And that's our work, shell fusion. Thank you very much.
Thanks a lot, Ciao. We can move to the last presentation of this session, that is by Antonio. Can you please share the screen? And it's about the generation of log statement.
Can you see the presentation?
Yes, feel free to start.
Okay. Hello, everybody, and thanks for being here. My name is Antonio Mastropaolo, and I'm a PhD student at the Università della Svizzera Italiana. And today I'm going to present you our work named Using Deep Learning to Generate Complete Log Statements. And without any further ado, it's time to start. Okay, so what are log statements, and in general, what is logging? Well, logging is a widespread activity among developers because it allows them to record valuable runtime information about applications. And specifically, each log statement is assigned with a log position, with a log level that describes the severity of the behavior that the developers want to track, and also with a meaningful log message. In order to support developers during these 3 different logging activities, researchers have been presented several approaches. For example, Log Advisor is one of these approaches, can support developer by suggesting them where to add a log statement. And recently, Lia colleagues presented a neural model, in this case DeepLV, that can fix and suggest already typed log levels. However, these approaches can be seen as a complementary approaches because they can only take care of one specific logging activity at a time. And for this reason, in this work, in order to overcome these limitations, we present LENS. LENS is the log statement recommender approach that can help developers by suggesting them where to add a log statement in a Java method, also by suggesting them which is the log message, and on top of that, also which is the right log level. We built LENS on top of the T5 model that was presented in 2019 by roughly colleagues from Google. The T5 model has a very interesting characteristic that it makes very suitable for the task that we aim at supporting. In our case, the task of complete log statement generation. And this characteristic concerns the overall training pipeline that I will describe you later. At this point, we can dive into the approach that we came up with to support this specific task. And first of all, we need a dataset for training our model. And to do so, what we did was to collect more than 5,000 Java repositories hosted on GitHub. After that, we extracted only these repositories having an explicit dependency towards log4j. From these repositories, we also extracted more than 6.7 million Java methods having no log statement whatsoever. And later, we also extracted more than 153K Java methods having at least one log statement. And after that, we ran our experiments and evaluation. Specifically, as I told you before, the T5 model has these very interesting characteristics concerning the overall training pipeline. And for the first one, the pre-training part, the goal is that we want to let the model to learn how to deal with the recurring pattern of the language that the model itself is working with. In other words, with a Java programming language, what we wish at the end of this pre-training phase is that the model has learned how to deal with the Java tokens. And to do so, what we did was to randomly mask 15% of code tokens in a Java method, and then we asked the T5 model to predict these masked code tokens. Then, during the fine-tuning, we want to specialize the model on the task that we aim at supporting. Again, we aim at supporting the task of complete log statement generation. And to do so, from a specific Java method, we strip away one log statement at a time, and then we ask the model to place back the entire log statement that we previously have stripped away. At the end of this process, what we have is a fully trained model that can support developers during the task of complete log statement generation. Specifically, this model can take as input a Java method and produces as output the same Java method with a log statement injected into it. The results that we achieved with this approach are the following one. Concerning the log level, we found out that length was correct in 66% of cases. For the log position, instead, we found out that length correctly predicted the position of a log statement in a Java method in 65% of cases. Instead, for the log message, length correctly generated the log message as a real developer would do in 16% of cases. And finally, concerning the most challenging scenario, the correctly predicted the log level, the log message, and also the log position. In this case, our approach was correct in 15% of cases. And with the results, I would like to conclude my talk. Thank you very much.
Thanks a lot, Antonio. So we can start the Q&A session. I ask all the speakers to have the camera turned on. Antonio, if you can stop okay, perfect, the screen sharing. Okay, so we have a bunch of questions in the chat. I will start from those, but from the audience, feel free to unmute yourself and ask questions if you have. So I will start from the first one that is in the chat from Hanyang. The question is from Kyuyan. This is just to remind everyone, the paper that basically evaluated different code review recommendation tools in industry. And the question is, I think the usage of the mean reciprocal rank is too strict and top K accuracy is ordering ambiguous. I think NDCG, which I think is normalized discount cumulative gain, from information retrieval is more suitable compared to top K accuracy or MRR. Do you have any thought about that? So this is for you, Kyuyan. You should unmute yourself. Wait, I can't hear you. Yeah, I mean the volume is very low. Can you speak louder? Okay, I would move. Okay, let's see.
Hi there, Han Yang here. So
Okay, now we can hear you.
I'm not the author, but I do see a lot of recommendation systems use two metrics to quantify the performance. One is top K accuracy, another one is the mean reciprocal rank. To me, I feel like NDCG is actually a sweet spot among those two metrics. And I'm not sure why top K accuracy and MRR are used.
Mm-hmm.
Is that a requirement for this track?
I don't think so, but Kyuyan, I don't know if you want to add. Can you try to speak now?
Can you hear me? Can you hear me?
Yeah, now
I
we can
open
hear
the
you.
page. So
Okay.
So please repeat the question.
The question
is by Hang Yang-Hu?
Yeah, Han Yang,
Yeah.
I don't know if you want to repeat it. Maybe it's easier.
Okay, I said the question. Okay.
I can repeat my question. Basically, you evaluate the effectiveness of your recommendation system using two metrics. The first one is top K accuracy.
Yeah.
Which I think is bordering ambiguous, especially in the K part. And the second one is very strict, which is mean reciprocal rank. I'm looking at the formula right now. Do you think NDCG score is better? Let's summarize those two metrics.
So could you explain for me what is NDCG?
Okay, so it's tough to explain this matrix, but NDCG starts from DCG, and DCG is discounted normalized gain. Discounted cumulative gain. Not sure how to explain the formula. I'm looking at NDCG formula right now, but essentially,
wait. I can say it later, and I can explain it for you. And because use the top K accuracy is very obvious. When the code review recommendation system and when the developer they select the candidates, and there is a UI, and they can say the top. You can see a list of the recommended reviewers. So if the top five, for example, top five, with the top five, they can get the correct code reviewers, and this metrics can evaluate how the algorithm works. So we use this metrics, and we can. Yes, we can evaluate NDCG later. Yes, but maybe now we didn't considering another evaluation approaches.
Yeah. Thank you, Chiu-Yuan.
Yes, it's very straight and obvious metric. Yeah.
Okay, since we have several questions, let's move to the next one. That is to Wang-Xin. Okay, so this is about the recommendation of good first GitHub issues. And the question is it possible that some of these good first issues are addressed by non-newcomers?
Yeah. The question. Actually, we find that it's a common problem for issues labeled as good first issues to be addressed by non-newcomers because these newcomers are already maintainers or take part in the project for a while, then they will be much quicker to find these easy issues to solve them than any other developers from outside of the project. So if they find it's just an easy task, they can just solve it by hand, and then the issue can't attract newcomers from outside. So it's a problem for GFI GFI
Okay, thanks a lot. Of course, if you want to follow up with the discussion, I mean, the person who asked the question, in this case, Shangguan, feel free to, okay, just unmute yourself. Okay, then we have a question from Alexander to Hongyu. They basically say, Konvalenko et al. Showed that reviewers recommended by tools are usually already expected by the developers, so this reduces the value of these recommendations. So to what extent can the hypergraph-based approach avoid this problem? So recommend reviewers that are basically not expected.
I think because I don't really see anything from the chat channel, so maybe I want to I need to repeat that question.
Okay, I'm going to repeat it.
You can reopen the page.
Yeah, okay, it's fine. I can repeat it. So the question is, there is evidence in the literature that these reviewer recommender tools often recommend as reviewers people that were already expected by the developers. So the developers already expected these people to be good reviewers for that change. Okay, and this means that the usefulness of the recommendation is not very high because they already had in mind those people. Okay. So the question is, can your hypergraph-based approach avoid this problem and maybe recommend people that were not really expected as good reviewers for that change?
Okay. So so basically, it's like someone has his or her Miss or Mrs. Right reviewers, right? He has an expected one. So, but if we just use the recommender, he will get he or she will get the one that he do not really want, right? That's the question.
Yeah, Alexander, I don't know if you want to provide more information, but I think the question is your approach? Yeah, okay, Alexander is connecting, so he can elaborate.
Yeah, so essentially,
the
ideal tool should not only provide correct recommendations, but also recommendations which are going outside of the expected ones, right? So things which are somehow new for developers, because otherwise developers are not going to use the tool because they already know who is going to who needs to review this pull request. So the question was whether you can somehow diversify or somehow achieve this kind of unexpected recommendations.
So we do talk. That's one of our goals to make a more diversified recommendation because we introduce some new metrics, and it's not our the designed goal for our approach, but our experiment has shown that our recommender can make a very relatively high diversified result, but still with the best accuracy. That's part of our experiment. And if there is, if someone has some preferred ones, or we just want to embrace with some new, the newcomers. So I think the recommender so far is still some kind of the semi-automatic tool, right? We are basically giving a candidate list. So, you can always try to find someone with that. And I think if we do want to introduce something like we want to embrace the newcomer or something else, we could just incorporate something like the feedback mechanism. Because we've already tried that in the requirements to code traceability. That's also part of my research. When people are going through the candidate list, if you like it or you don't like the candidate trace, then your choice will impact the remaining of the unidentified traces. So we can always do something with the user's feedback.
Okay, thanks a lot on you.
Okay, thanks.
Thanks, Alexander. Alexander is, if you want to follow up, otherwise I'll move on.
Yeah.
Okay. So there are other questions for you, but I will skip them because I want to ask questions to everyone, and then if we have time, I come back. Okay. Otherwise, please
I have some time
chat.
for the refresh. Okay, refresh.
Yeah. Okay. Okay. Sounds good. Okay. So I would move to a question for Chao about Shell Fusion.
Yeah,
so the question is from Martin. Martin, maybe you want to ask it directly because you are one of the speakers.
Yeah, sure. So in the approach, you use TF-IDF for similarity comparison, but you also have a embedding model. So what is the rationale for using TF-IDF when you can build an index using the embeddings directly and have the comparison between the embedding of the query and the embedding of the documents?
Yeah, I understand your question. And word embedding is a common to mirror the similarity. And we test the TF-IDF, and we found that in some cases, especially for the data features, we found the query and the description have some features, or we can just use the TF-IDF to simply mirror the similarity, and finally we found that combining two of these methods is a better choice. And the second question you gave, whether the deep learning model is a better choice, I think maybe because we just want to find a simple choice, because the Shell Fusion, Shell programming answer generation work, the difficulty, the most difficult part is the data analysis and how to fuse, and maybe learning is not the most difficult part. Yeah.
Thank you very much. That makes sense.
Yeah, thank you. Thank you.
Thank you both. So before moving to the question for Antonio, I actually have a question for Martin that concerns one of the points that I already had this question for you, so I want to know your opinion. So first of all, I'm completely with you, meaning that I also believe that to improve the performance of deep learning models, you need this multimodal representation. You need multiple representations of code because they provide you different information. But I was also wondering what is the overhead, right? Because you have two different overheads here. One is in terms of training time, I guess. And the other one, it's also in terms of data extraction, because one thing is to just say, well, I flattened source code, this is the stream of token. And another thing is to say, well, I need to parse. Maybe you need code that is syntactically correct if you want specific type of representations. So what was the gain and what was the additional effort? What is the trade-off there? Because you know better than us.
Yeah, that's a very good question. And I think we can make a link with the trend with the scaling law. Because currently we have this large pre-trained model, and the more we scale them, the highest the performance are at inference, right? Mm-hmm. And so I would say that something that is important on the one hand would be, can we have the multimodal learning pre-trained model that converge faster than the unimodal learning, and that scale also, as well as the unimodal learning. Sorry. So this is something that needs to be empirically studied, I think. And for that we need more multimodal learning approaches to code modeling. So that's one thing. The other thing about the data extraction. So of course, I would say the overhead here is not about the training, because when you use a graph neural network, the number of parameters you get in a graph neural network is nothing compared to a transformer.
Makes sense.
So I would say that in the training, there's almost no overhead in terms of resources. However, there is an overhead in terms of extracting like the concept graphs in our approach. So we have to define what is a concept graph, what are the relationship we want to extract. So that's quite a tedious process. And the other thing is the combination, because it's not straightforward to combine a graph neural network with a transformer. Here in the approach that we show, it's quite straightforward because they are simple encoders. Mm-hmm. But if you have an architecture like encoder-decoder, then it's a bit more complicated, for instance.
Yeah, sure. Okay, great. Thanks a lot. So I'm going back to the chat. There is a question for Antonio from Alexander that basically says that in 85% of your predictions, you are not able to generate I think it was the correct log message. But would this wrong, let's say, prediction still be valuable? Did you look into them?
Mm-hmm. Thanks a lot, Alexander, for this question. It's very interesting because what we did in our work to shed light on this aspect actually was to sample 300 wrong predictions. And in this case, a wrong prediction is given by a log statement in which the log level and the log position were correct, but the log message was wrong. And what we found out after manually inspecting this wrong prediction was that in more or less 28 to 29% of cases, the log message that Lens suggests was still meaningful for developers. And to give you even a better understanding of what I'm talking about, I prepared backup slides that I have right here and I want to show. Okay. Can you see the screen?
Yes.
Okay. Wait a second. Can you see the slide?
No.
Okay. Just a second. Let me skip it. Okay. Now you should, right?
Now we see. Yeah.
Okay. In this slide, for example, in gray on the bottom, what we have is the log statement, the target log statement, while in bold, in black, we have the one that Lens recommended. And as you can see, as I told before, the log level and the log position are the same, but the log message is different. And specifically in this case, our approach, Lens, not only was able to correctly suggest something that was meaningful, but it seems that it really improved what the developer has written, because the target log message, it says, could not delete subscription 4, while the Lens log message is the exception trying to delete subscription configuration and so on. And given the context of the entire method and specific of the code snippet, in this case, this log statement is within a try-catch, it seems much more accurate. So yes, we this aspect, and there are a lot of predictions that, of course, are still, as I said, meaningful for developers.
Okay, thank you. There is another question for you in the chat. Please answer it there because we will not have enough time. Okay, I want to go back to Hongyu because he has 2 more questions in the chat that I think are related, that are about the representativeness of the data given the 12 projects. How do you select these 12 projects, and if those are all projects from GitHub?
Okay. So we choose the 12 projects because we have like 6 baselines, and we want to make sure that the project appears at least in each 2 of the baselines experiments. So that's so in overall we read an SLR article, and it's concluded like about 28 projects. So we make some selections, and we want to focus on collecting data from GitHub. So finally, we leave with like the 12 projects in our experiments. So yes, they are all from GitHub. And
okay. Can you adapt the approach to projects that don't use GitHub?
I think because the structure of our hypergraph is not that complex and dependent to GitHub. As long as you have contributor, you have PR, you have the reviewers, that would be fun, right? So we don't really do the we don't really move our experiment to the Gerrit platform. It's simply because collecting data from two different platforms, it's kind of nasty, and you have to put everything consistent, something for that. And we have some additional things to discuss for Martin's question is that the time, because we actually the